that you're not within their tolerance. But like I said, always, if you'll post those to Piazza, then I can look at them, because it's an individual student issue. And if it happens to affect more than one student, I can also see that. So good question. And as you know, if there is a problem and you're the first one to report it, then you get a bonus point, number one. And secondly, it lets me fix it so that other people don't get affected by it. And by the way, Mia, I have your lab notebook if you've been looking for it. Yes, I posted a note to you yesterday, day before yesterday. Yeah, you ought to sometime, especially if you're missing something, because I got it. There you go. Bam. All right. So we are continuing on in chapter 12. Chapter 12, to be honest, in some schools, they teach with 2045. We consciously don't. And the reason that we don't is because the concepts in chapter 12 reinforce the ideas that we see in chapter 17. And so that's why we pull those out a little bit differently. So let me go ahead and share my screen with you, and we'll get rolling here. All right. So sections 12.1 to 3 was on your video. And so I'm moving on with 4 today. Chapter 4 talks about Henry's law. Henry's law says that the pressure that you apply on a system affects the solubility of a gas. That the concentration of gas that you can get to dissolve depends on a physical constant that's specific to the gas. And so Henry's constant really is looking at physical, structural effects. We learned back in the previous sections, the like dissolves like thing, that polarity is one issue. But the other issue is that structurally, what does like dissolve like mean, by the way? Polar dissolves things that are polar, and nonpolar will dissolve things that are nonpolar. Doesn't mean that there can't be interactions between them and some dissolution. It just means that if you're going to have a large quantity of dissolution, they should be similar polarities. The more similar they are, in fact, in structure, the more likely they're going to dissolve in one another. And so Henry's constant says, if I look at the structural effects and the polarity of the specific gas, then I can describe how it's going to interact with the solvent. And so since we're talking about the solubility of gases in solution in water, then Henry's law is talking about that. It says that whatever the pressure is that you apply, it's going to create an increased concentration. Some gases are more soluble than others. You can see, for example, that oxygen is much more soluble than nitrogen or CO2. But in all cases, gases are all more soluble at higher pressures. Now, this is actually the source of the bends when you're diving, because typically nitrogen is not terribly soluble. 90% or 79% rather of the air you breathe is nitrogen. And under normal pressure conditions, it doesn't dissolve very well in your blood. Notice that it has a fairly low compared to oxygen solubility. So oxygen dissolves, nitrogen not so much. But if you increase the pressure by going at depth, and you may remember from your 2045 discussions, every 32 feet you go down under the surface of the water, you're adding 1 atmosphere. So you're changing the pressure on the gases specifically, and therefore you're increasing the amount of nitrogen that can dissolve. Now, as long as you're still down there at depth, it's not a big deal. Problem is when you try to come back up, because you have to give your body time to re-equilibrate for the new pressure conditions. And you have to have all that nitrogen, you have to exhale all of that. And so that's why when you come up, they give you a certain amount of time at each climb that you need to spend just to exhale this. The bends is actually usually because you have tiny bubbles that have formed of the gas. It's no longer soluble. So now you have bubbles that are formed in your bloodstream. It's very, very painful in your joints, but it also can stop blood flow. As you know from your titration lab, if you get an air bubble in your burette, the water doesn't flow. Well, the same thing happens in your capillaries. If you get a bubble in your capillaries, then it stops blood flow. And so the other thing that happens, of course, as you increase or as you get up towards the surface is you are allowing that bubble to expand out, because Boyle's law told us that as the pressure is decreased, then the volume of your sample, if it can move, will increase. So the bubbles are getting bigger. They call it the bends because people are in such extreme pain that they're bending over trying to find a comfortable position. Most people honestly don't survive the bends. If you are a diver and they tell you you shouldn't fly within a certain number of hours of a dive, even if it's not a very deep dive, they're not kidding, because there are people that get the bends in the airplane because the pressure is much, much lower there. And so now those bubbles have gotten a lot bigger. So even though on ground they weren't having much of an issue, in the airplane they can. Excuse me. So quick calculation here. What's the concentration of nitrogen that can dissolve? If it's saturated at 2 atmospheres, it's just a plug and chug. Our Henry's constant for nitrogen and our pressure, 8.42 times 10 to the minus 7. Now pay attention to units. That's the only thing in this section you need to be careful with. It's molarity per millimeter of mercury. Our pressure was 2.0 atmospheres. And we know that for every 1 atmosphere, there's 760 millimeters of mercury. So it's a simple substitution. So if you're going to store your bottle of seltzer or even soda, when you open it, it fizzes because the pressure's been released and then the gas can escape. So how should you store it if you don't want it to go flat as quickly? You should cool it. That's why people typically store their beverages once you open it in the refrigerator. If you leave it out on the counter, it's going to go flat faster. What else? You should absolutely increase the pressure because that will keep it dissolved in the solution. Otherwise, it's going to escape. So they actually do sell these little pumps so that you can store it under pressure. Is it very effective? Not really. In part because once you've opened it, the CO2 gas has escaped, and that's what you wanted to go back into solution. And so if you recharge the bottle with CO2 gas and then pressurize it, then yeah. But keep the cap on, at least. That keeps the pressure somewhat contained. Which brings us to an idea that's absolutely a high school chemistry idea. It's just that you haven't practiced with converting between different units of measurement very much. So when we're talking about solutions, we talk about solute, which is present in the least amount, or lesser amount at least. You can have more than one solute. Your tap water does. You have calcium and magnesium probably. If you have hard water, you have sodium. You've got all kinds of stuff dissolved in your water. So solute is any substance that's present in a lesser amount in your mixture. Solvent is present in the greatest amount. And so if you're talking about air, for example, solutes might be things like oxygen, because the largest quantity in air is actually nitrogen. So air is only portion that's oxygen, but 79% of it's nitrogen. If you're talking about aqueous solutions, of course, then your solvent is water. And this is pretty much anything else that's dissolved. So the solution, of course, is a mixture. Sometimes people forget to pay attention to that, which means that this would be the solute and the solvent. Notice the common abbreviations that we use for those things. Now, the reason I'm sort of emphasizing this is, one, of course, the terminology matters. But in this chapter, if you ignore whether you're talking about the solute or the solvent or the solution, then you're not going to be able to solve any problems. So you just need to label very carefully. Of course, back in high school chemistry, you learned about molarity. Molarity is moles of solute per liter of solution. Problem with molarity is that it changes with temperature because volume is sensitive to temperature. So while we like it, it's very convenient as long as we're working at a constant temperature. Most of our calculations for things where conditions might be changing or involve other units of concentration. So most of the time your concentration is talking about how much solute there is to solution, but how they describe it is not always solute to solution. So let's look at a couple other units of measure. Some of you you're not as familiar with. Molality, lowercase m. It's underscored if they can't bold it. So if you ever wonder why we typically write molarity with an underscore, it's because people don't want to have to take the time to bold every time they write the M. And so we underscore it and everybody knows it's the same thing. Same thing for molality. Molality is moles of solute, now pay attention, per kilogram of solvent. He's a real weirdo. He's compared to everybody else, or he's different from everybody else because he's the unit that doesn't care about the overall solution. He cares about the relative ratios of the things involved. Yeah. Most of the time, to be honest, when you're talking about physical processes. And so we're going to be doing some today, and you're going to find that when it, with your freezing point depression lab, it's the only unit you use. So it's very common because, again, it doesn't depend on volume, and it's based on just the quantities of things that you have involved. Mole fraction you actually did talk about back in Chem 1. You were looking at gases specifically, but mole fraction is just the moles of whatever component you're talking about compared to the total moles. When we were talking about moles, mixtures of gases in Dalton's law in 2045, then we used mole fractions. It's typically written as sort of a chi instead of just an x, but for convenience sake, we're just going to use an x here. Now, it doesn't specify which component. Pay attention to that. You could describe the mole fraction for the solute, in which case it would be the moles of the solute over the total moles solute plus moles of solvent. It could also be mole fraction of solvent. And that would be, of course, moles of solvent over the total, which is moles of solute and moles of solvent. Now, of course, if you think about it, we know that all the sum of the parts of a solution has to equal 1. So if I've solved for 1, I could say 1 minus the mole fraction of my solute would give me the mole fraction of my solvent, because they have to add up to the whole. To be honest, most of the time we care about this one. However, if you're given a solution in other units, we probably are going to need to convert it to this form and then relate it to our solvent. So this one is the most useful. However, it's not uncommon that you're asked to solve for that one. Percent by mass. Mass of solute over mass of solution. Now you might wonder why when we talked about mole fraction, we didn't talk about moles of solution, and that's because a solution isn't a pure substance. You can only have moles of a pure substance. So we can talk about total moles, but we can talk about moles of individual things involved. And you've done percent by mass before. To make it into percentage, remember that percent is to 100 as our part is to the whole. It's just in this case, the part we typically care about is our solute and our whole is our solution. Now, since we're talking about masses, remember that your solution is solute plus solvent collectively. So if I want to solve for percentage, you can see that my percent is to 100% as part is to whole. If we multiply by 100%, then we're going to come up with a percentage of that particular thing. Now, if your concentrations are extremely low, then we talk about parts per million and parts per billion. And there is parts per trillion also, but these are the ones you're responsible for in this class. It's exactly the same ratio. It's exactly the same ratio. It's just the difference is what the relative quantity is. Part per million. Per means divided by million. Is equal to the mass of your solute over the mass of your solution. So if I want part per million, then I'm going to take that same fraction and multiply by 1,000,000. Just like when we want a percent, we multiply by 100 because cent means 100. 100 years in a century, 100 cents in a dollar. Parts per billion times 10 to the 9th, same fraction. So if you can set up the ratio for percentage, then it's just changing what your multiplier is when you want to know about parts per billion. Now, very commonly, you will see this as a substitute. This is approximately the same. So let's talk a little bit about why that is the case. If I have a 1 milliliter solution and it is very dilute, then I can say it's essentially the same as 1 ml of the solvent. Because if it's extremely dilute, it means you don't have very much solute. So that 1 milliliter is mostly solvent. And if we're talking about aqueous solution, there's 1 gram per milliliter. So we're approximately talking about 1 gram of water. So now if I compare my microgram to my 1 gram of solution, because my solution is mostly water, then I have a 10 to the minus 6 to 1, or a 1 over 10 to the 6th ratio. It is a part per million. So this is a nice little shortcut if you're talking about a very dilute solution, but it's because of this. We're actually going to work around it so that we don't have to do that most of the time, because we would like a more precise definition of it. But a quick seat of the pants, if you're in the lab and you just want to know how many parts per million, you don't have to do a lot of calculation, and you happen to have this data available, okay, you'll have it. But remember, it's an approximation. It's not a a definition. So what I'm going to do today is sort of organize your thoughts about concentrations, because one of the first tasks that you're asked to do in the chapter is to be able to convert between the different units. As we progress through the chapter, you'll see that different properties of the solution depend on the information in different units of concentration. And so we need to be able to convert what we have on the label to what we need to know. First thing I wanted to really emphasize for you is that concentration units are a ratio. Always, always, always. You tend not to think about it that way, but it is. For example, if I'm given a 6 molar solution of HCl, there's an implied ratio that says for every 6 moles of HCl solute, there is 1 liter of solution, by definition. So when you're given a concentration, it's very helpful to write it as the fraction that it is. It will show you how it's used, for one, but also it will remind you what information it's really talking about. Just as a reminder, we name our solutions by the solute. If we're talking about aqueous solution, everything's in water. Naming it by the solvent would mean that every solution is called dirty water. So we want to know specifically what was different about this one. So what we know here is that we have a 1 molar solution of KCl. And I want to know, what are the other ones? Okay. Well, I know that molarity means that I have 1.0 moles of KCl for every 1 liter of my solution. So take the time to rewrite it because it'll help you out. Then I set up a little chart just to keep organized about what I'm talking about. Am I talking about the solute? In this case, that's KCl. Am I talking about the solvent? In this case, it's implied to be water. If they don't tell you otherwise, if you're talking about a solution that's or a solution that's probably going to be an aqueous solution. Or am I talking about the solution itself? And in order to go between the different units of concentration, it's helpful to sort of organize what I know. Typically, I need to know about mass, I need to know about moles, and there's some reference or conversion information. For pure substances, my reference information is going to be molar mass. And for my solution, my reference information is going to be my density. So when I'm given a ratio of 1 mole of KCl for every 1 liter solution, it means that I know 2 pieces of information. Now, the solution is the only one that we need a volume on. And I usually just make a column here for the volume. So what I know about the solution is that I have 1.0 liters. Very often you need to know milliliters, and so that's why I make a place for that as well. So solution is the only one that has a volume that you need to be concerned with, which means that I have 10 to the 3rd milliliters. So if I need to know all of these others, I'm probably going to need all of these bits of information. So that's why I just go ahead and set up a chart to organize my thoughts a little bit. I've got KCl, 39.09, 35.453, .543, my molar mass for KCl, 18.0158 for water. I use that one a lot. Now in this case, they gave me the density of the solution as 0.99 grams per milliliter. If you're not given a density, assume that the density is 1, but write it down. Anytime you make an assumption, write down why you're making that assumption. So what could I find based on the amount of information I have right now? Because I'm talking about mass and moles here, and volume only applies to solution. So I just made an extra column there for the volumes. Everybody else was talking about mass and moles. Good question. So what could I calculate at this point? Absolutely. If you have 2 of the 3 things in a column, you can always find the third. I've got 1.0 mole. I know that for every 1 mole, there's 74.543 grams of that substance. So 74.543 happens to match the mass of my KCl. Now there's something that I can find about my solution. What is it? Sure. I've got a density that talks about milliliters, and I know how many milliliters I have. Would you agree to that? So if you have milliliters and density, you can always find grams. I have 10 to the 3rd milliliters of solution. And I know according to my density that for every milliliter, there's 0.99 grams. So I must have apparently 990 grams of solution. Where can I go from there? Well, I can't find moles of solution because it's not a pure substance. I know that moles in terms of my solution is moles of this plus this. So these two have to sum to give me this one because there's no such thing as moles of something that is not a pure substance, but it's the moles total. So you're exactly right about that. What else could you find? Mass of the solvent. How would you do it? Sure, because we know that this is a total. In fact, the way I set up my chart, this plus this always has to equal the one on the right. So 990 minus 74.543 gives me what? 906.15.457? Yeah, grams. Now what could I do? Find the moles of my solvent. I've got 915.457 grams. I know that there's 18.0158 grams for every mole. $50.8141. Now I can find moles total. 51.8141. Now, I've never seen any textbook that does this, but I find that if you know that you're going to have a question where they're asking you between all the different types of units, you can fill out this chart, and then you have everything you need to be able to set up any other unit of measure, because you're always given two starting places. The number one error that students make is they forget the denominator, and then they're missing information. But there's always two starting places, and you can populate all this. Then we can substitute into our definitions: molality, mole fraction, percentage, parts per million. Molality means how many moles of solute, solute per kilogram of solvent. Well, I know how many moles of solute. I know how many grams I have of solvent, so I must have 0.915457 kilograms. Unless your density is very different from 1, your molality and your molarity are going to be very similar. And so just a quick rule of thumb is they should be fairly similar numbers. If they're not, then you've made a math error somewhere. I'm just going to set these up here. Now with mole fraction, we can set it up based on anything. If I based it on KCl, then I'm going to label it that way. If I base it on my solute, moles of solute that I have are 1.0. My total moles is 51.8141. So mole fraction is going to be a fractional number. It's going to be a decimal always. Percent is based on mass. It's going to be the mass of the solute over the mass of the total solution times 100, because that's what percentage is all about. I know that my parts per million are, I'm a little excited there, should be same fraction, mass of solute over mass of solution. But because it's per million, we're going to multiply by 1,000,000. So based on our numbers, what's the mass of my solute? And what's the mass of my solution? 990 grams times 10 to the second. And if I take my percent and multiply it by 10 to the fourth, then I'm going to end up with my parts per million. Would you agree to that? Because it's exactly the same fraction, just 10 to the fourth times larger. Are you with me? Did I miscopy a number? Right. I just can't read my own writing. Thank you. So the challenge here is to make sure that you have figured out all of the information you're given and then how these things relate to each other. So let's, notice again, your molality is very similar to your molarity. It was 1 molar, it's 1.1 molal. That's how you pronounce that. So next one says, well, what if you're given a molality? Okie dokie. You're going to do the same thing. Remember, molality tells us how many moles of, in this case, KCl, for every kilogram of solvent. So there's an implied 1 kilogram in the denominator. Solute, solvent, solution, and then there's a column here just for volumes because that's only talking about the solution. That was the same number, yeah. Since our solute is still KCl, it's the same molar mass here. Solvent is still presumed to be water. They would have to tell you if it was something else. And we're told a density here, 0.98 grams per milliliter. So my starting information tells me that I have 1.0 moles of the KCl, and I have 10 to the third grams of water. Because again, it's 1 kilogram or 10 to the third grams. So where can I go in one step? Sure, I can figure out the mass of the solute because it's the only thing I don't know in that column. I have 1 mole times 74.543 grams per mole. Where can I go from there? Sure, because I know that the solute plus the solvent will always equal whatever's in my solution column. So 1,000 plus 74, 1,074.543 grams. Now what? Sure, I can find the moles of solvent. I've got 10 to the third grams, according to my molar mass. For 18.0158 grams, there's 1 mole. .5068. Now what? Absolutely. I can get my moles total, 56.5068. But for one of the concentrations, I need volumes. So how do I get to volume? Absolutely. For the solution, I have grams, and this tells me how grams relates to milliliters. So I've got 1,074.543 grams. And apparently for every 0.98 grams per milliliter. That was a 96. .47 milliliters. And in liters, that would be then divided by 1,000, 1.09647 liters. Now I'm keeping lots of sig figs here because I don't want to introduce a rounding error, even though I know that I'm not really entitled to all that. I only had 2 sig figs at most, but in your intermediate information, keeping 4 at least is a good place to go. So the rule of thumb is keep 2 extra insignificant digits till the end of your problem. So now I can set up my definitions. Molarity, mole fraction, percent, and part per million. Molarity is moles of solute per liter of solution. So 1.0 moles for every 1.09647 liters. Mole fraction could be based on any of the substances. So I'm going to base it on KCl this time, and we'll look at that one in just a second. Mole fraction is a ratio of moles to the total moles. I have 1 mole of my KCl, and my total moles are 56.5068. How do I calculate my percentage? Mass of solute over mass of solution times 100. And for parts per million, it's that same ratio times 10 to the 6th. So in this instance, 74.543 over 1,074.543 times 10 to the 2nd. Whatever that answer is going to be times 10 to the 4th. Again, that's just the difference between those two. And just substituting in directly into the definition, you can see that, yes, it always ends up being just 10 to the 4th times larger when you're talking about parts per million. We calculated the mole fraction based on the KCl. If I needed to know the mole fraction based on my solvent, how would I find that? You absolutely could just set up that fraction, or you can say 1 minus the mole fraction of your KCl. Because you know the mole fractions have to sum to 1. So either one would get you to the same answer. Just depends on which one you want. So 0.0823 if you're asking about the solvent. And again, that's the one we usually work with, but as long as you solve for one of them, you can always easily find the other one. At the risk of beating a dead horse, I'm going to do a couple more of these. This is something that you need to be very comfortable working between the units. And so I'd expect a quiz on Tuesday over these topics. It's that important. And you can go back and track the video to go back through the process, but you need to try a few of these because they're not hard, but it's all about knowing those definitions. All right, so let's look at the next one. What we're told this time is that we have a mole fraction of KCl that's 0.060. Again, that's a ratio, 0.060 to 1, because anything could be written as a fraction over 1. What's in the top? What are the units on the top? Moles of my solute. And what's on the bottom? Moles total. Again, label everything when you rewrite it, and then the problem becomes fairly trivial. So our solute is, in this case, KCl. Our solvent is presumably water. What we know to start with is that we have 0.060 moles of KCl and 1 mole total. Reference information here, 74.453 grams per mole because it's the same solute. 18.0158 grams per mole because we're talking about water. And the solution density was 0.87 grams per milliliter. And I probably need to know something about the volume in order to solve the rest of the problem. So what should I do? Okay, I can find the mass of KCl. I have 0.06 moles. And I know that for every mole, the mass is 74.453. Okay, 4.4672 grams. Where else can I do? I can find the moles of water. How am I going to do it? 1 mole minus the 0.06 moles of my solute gives me 0.94 moles of the water. Now what? Mass of my solvent. I've got 0.94 moles of it. And I know that I have 18.0158 grams for every mole. $16.9349. Now what? Absolutely. 4.4672 plus 16.9349. $1.4021. Now what? Volume solution. How am I going to do that? Absolutely. I've got mass in grams, which means I can use my density to convert it to milliliters. 21.4021 grams. And I know that for every 0.87 grams, there's a milliliter. So if that's liters, 0.024601 liters. So I'm asked for molarity, molality, percentage, and part per million. Just to mix it up a little bit, we'll make that part per billion. What's the definition of molarity? Moles of solute per liter of solution. Yeah, I know it, and I personally don't have to write the definition every time. What do you think I'm doing it with you? Practice, practice. If you're working on these, label them yourselves so that it becomes natural, so that there's never a question in your mind what units go with that. So our moles of solute, 0.060, liters of solution, 0.024601. What's the definition of molality? Moles of solute per kilogram of solvent. So 0.060. What we have up here was grams. So 0.0169349 kilograms. How do I calculate percentage? Mass of my solute over mass of my total solution times 10 to the second. Same fraction times 10 to the what for parts per billion? Parts per million is 10 to the sixth. Parts per billion is 10 to the ninth. So if I get this, the difference here times 10 to the seventh would take me between those. In this case, 4.4672 divided by 21.4021. In this case, the molality and molarity are not as similar because the density is a lot different from one. So don't be terribly surprised, but they should be a similar magnitude. I wanted to calculate the mole fraction of my solvent. How would I do that? Absolutely. So we were given 0.06 as my mole fraction. So apparently 0.94 for the solvent. Yeah, they're both in the ones place. It's twos and threes. They're similar in terms of which place they're talking about. Magnitude is typically what multiple of 10 you are. These are both 10 to the 0th in terms of scientific notation, as opposed to the percentage, which was 10 to the 1st. Different magnitude than either of these two. So these two, molarity and molality, should be similar numbers if the density is pretty close to 1. It's not going to be exact, but it's going to be close. It's going to be similar. The farther away the density goes from 1, they're going to start varying more, but they should still be a similar magnitude. They're both in the ones place. It's going to be very different from the other units. So it's just a couple things to sort of check and see if you're on the right track with what you're doing. And I know you're like, seriously, Nance, can we be done with this? I know it's tedious, but I'm doing this for a very good reason. Again, it's all about remembering what you're told. When you're given a percent, there's an implied denominator. What does per cent mean? Per means divide by 100. Right? That's what that is getting at. So in this case, we are given a 1.05% KCl solution. That means that we have 1.05 grams of KCl per 100 grams of solution. So all of the other units, molarity, molality, mole fraction, all have 1 as your denominator when you're given that. But remember that percent, parts per million, parts per billion, all have different denominators when you're given them. So just be very, very conscientious with that. And that's why I am walking through this last example. So even though they all pretty much act the same, it's the starting point that's different. So when I'm given a percent of KCl, presumably in water, it's important to recognize what they've given you. A percent means any percentage they've given you is based on a 100 denominator. So I've got 1.05 grams of this and 100 grams of that. So where can I go in one step? Easily. 100 minus 1.05 gives me my mass of water. What else can I do? I can find moles of the KCl or of the water, 1.05 grams of KCl, and I know that for every 74.543 grams, there's a mole of KCl. Do the same thing for my water. else can I find? Absolutely. And that would give me my total moles. Now what? Mm-hmm. Everybody understand how I'm setting these up? Remember, I have grams on top, so that means the grams have to be on the bottom to cancel. Basic dimensional analysis stuff. Again, molarity means what? Moles of solute per liter of solution. Molality means what? Moles solute per kilogram of solvent. How do I set up my mole fraction? Absolutely. Moles solute over total moles. 0.0141 over 5.5065. And if I needed to know my solvent, it would be 1 minus whatever that one was. How do I set up my part per million? Mass solute for mass of solution times 10 to the 6th, because parts per million is to a million parts per million as the mass of your solute is to the mass of your solution. That's why we end up multiplying by 10 to the 6th. So the one that's tricky is everybody else has 1 as the denominator. You need to remember that per thing means something when you're starting out with these values. So substituting in some of my numbers here. So I know it's a little bit tedious, but it's just something that you need to practice to get comfortable with. Now, occasionally, you'll see a problem where they'll only ask for one of them. And so you still can use the same idea. It's just that you need to figure out which boxes are going to be relevant. Let's look at this one. We got 3.5 molar. We have a density of 0.997. We got sodium chloride, which is 58.44 to save us some time. We got water, presumably 18.0158. We've got our solution with a density of 0.997. Just to see to the pants piece of information, if my molarity is 3.5, this one doesn't make sense, and neither does that, because the magnitude is not similar. Molarity and molality should be similar numbers. Now, it may be that none of these are the correct answers, but we can at least eliminate A and C instantly. Since it's molarity, what does that tell me? What two pieces of information can I get from molarity? Sure, that's moles of KCl per liter of solution. So I know that about my solution, I have 1 liter in terms of volume, and I know that I have 3.5 moles. If I have 1 liter, of course, I know how many milliliters that is. That's 10 to the third. What else do I know? What do you think, Carlos? What should I do next? How am I going to do that? Yeah, sure. The molar mass. So I've got 3.5 grams times, I'm sorry, 3.5 moles. Sorry. And for every mole, there's 58.44 grams. Four, 5.4. What can I do next? You think, Taylor? Well, bearing in mind this is grams per milliliter, where could I go from there? Absolutely. So remember that density is mass over volume. So if I need the mass of solution, it's going to be my volume times my density, 10 to the third milliliters, 0.997 grams per milliliter. Gives me 997 grams. Where can I go from there, Michael? Absolutely. I've got 998 grams total. If I subtract out the water, oops, 79, 793.46. Now what? do you think, Paige? How am I going to do it? Sure. 793.46 grams. And I know that for every 18.0158 grams, there's a mole. Okay, 4.0425. Mia, what should I do next? Absolutely. Because I know that if I have either of these two, I can sum to my total. So 47.5425. So my molality should be 3.5 over, again, kilograms, 0.79346. Apparently, none of these. Don't even have to bother with the other ones. Oops. Because I know that my molality should have been this value. Are we okay? So look, oh look, somebody even predicted that you were going to have a quiz over that. Throw it in your notes. Oh, I said Tuesday, didn't I? I'm going to give you till Tuesday. I want to give you a little bit of time to practice those. So look, somebody even predicted this. So we're shooting for Tuesday on this one, and it's an important skill set. It'll be in class. It'll be pretty much, I give you a piece of paper that's says something like this. All right. Where we're headed today, we're doing the FPD lab today, right? That's what in my head, that's where we should be going. FPD, freezing point depression. Freezing point depression is one of these colligative properties. And so we're going to talk a little bit about that. Colligative properties in general depend only on the quantities, but not the identity. Of an impurity. There are some characteristics, physical properties of solutions that have nothing to do so much with what the substance is. It's just that any contaminant would cause a similar effect. Among these things are things like freezing points and melting points, and things like osmosis and dialysis. All of those are a function of just how many particles they are. It doesn't really matter what the particles are. It just matters that there's a different number than there would have been before. So colligative properties depend only on quantities, but it doesn't depend on what the substance is. A couple other words we use here. Volatile means that a substance is easily converted to a gas. Vapor pressure is the pressure that builds up in a sealed container over a liquid. You guys have experience with this. If you have a bottle of rubbing alcohol and you just loosen the lid, then it typically hisses at you, especially if it's been sitting in a windowsill. that's built up some pressure because alcohol is fairly volatile. It likes to go into the gas phase, and therefore it will build up pressure. Now, things that are volatile will build up higher vapor pressures. Than non-volatile substances. But vapor pressure is also temperature dependent. Vapor pressure increases with increased temperature. And that's stuff that you've seen before in 2045. That as you increase the temperature, you're making the particles move more quickly, which means that some of them can escape into the gas phase more easily and break away from the surface tension and become a gas more easily. So as you increase the temperature, you expect to have a higher vapor pressure. Normal boiling point is a temperature. Again, it's not a point, it's a temperature at which the vapor pressure equals 1 atmosphere. Common. Typically in literature, you'll see this next to something they're telling you it's volatile when they're describing a substance. Boiling point elevation and freezing point depression are colligative properties. Boiling point elevation says that any impurity will increase the boiling point of a liquid or of a substance. And freezing point depression says any impurity will, give you a hint, it's depressing, decrease the freezing point or melting point. Freezing point and melting point are the same temperature. Now, of course, the process of it is actually a fairly simple idea. Let's say that I'm looking at boiling point. In order for something to boil, the particles have to move fairly quickly so that they can break apart. So now I've got them moving fast enough, they're breaking away from their peers, they get to the surface, and there's all this atmospheric pressure that's pushing down on them. So in order for something to boil, it has to move fast enough to overcome the intermolecular forces. And secondly, and that's where the temperature part comes in, secondly, it has to build up enough pressure, or build up enough energy, I should say, to overcome atmospheric pressure. And then finally, it can escape into the gas phase. Now, let's say that it never gets to the surface. That I have this extra molecules in here that are blocking the surface of it. So even though they're moving fast enough, and they theoretically have enough energy to overcome it, if they can't access the surface, then they can't escape. And that is where the impurity comes in. Any impurity that you put in there has the potential to take some of that surface space. So when you're boiling your pasta water, They typically have you add salt to it. It's actually less about flavor because if you think about it, you then drain the pasta and rinse it, and it's not really embedded into the pasta particularly. It's really more about just interfering with the ability of the liquid to actually get to a boil. It's covering the surface of it so that it can't build up that vapor pressure. So it can't do what it needs to do. And so any impurity would do that. It just is blocking the surface. That's why commonly they'll also tell you to use oil. Oil does a better job. It masks the surface completely if you have enough of it. Oil does have a residual effect on the pasta because as you're emptying the pasta water, then the oil's coating the surfaces and makes them less likely to stick together. But to be honest, it wouldn't have mattered what substance you added because, again, it's colligative. If I had an equal number of particles of sugar, then my temperature would be affected in an equal way. It's all about how many particles you have. Now, when you think about freezing point, it's a similar issue. In order for something to freeze, the particles must get close enough they have to be moving slowly so that they can reestablish their intermolecular forces. So what if the particles can't get close to each other because there's other stuff in the way? Then it's going to delay their process of freezing. So one of the first things that we track with colligative properties is Raoult's law. And Raoult's law says the vapor pressure of a solution varies as a function of its purity. Now, it depends on what's in it. When we talk about Raoult's law here, we're talking about mole fraction typically of the liquid itself. Because only something as volatile could actually develop a vapor pressure, somewhat volatile. So mole fraction of solvent is the part that we care about. The more of that substance we have, the more vapor pressure we could theoretically build up. P with a superscript 0 is the vapor pressure of the pure solvent. But there's actually a couple different forms. This one says I only have one volatile component. But what if the impurity that I add is also volatile? Well, if that's the case, then they can each contribute. Where this is the mole fraction of maybe the solvent, and then we have our volatile component, solute. So each of them can contribute to the overall vapor pressure that we observe. This is the function of antifreeze in your car. If we can keep the vapor pressures down by introducing an impurity, then we can heat that water, that coolant water, more and more and not have it boil off and not have it build up a lot of pressure in the system. So that's really why we use antifreeze, is to keep the water from boiling off. So how will I know which one to use? It just depends on whether or not I have a volatile substance. I only have one substance that's volatile, or do I have multiples? So you just need to read through the question. 2-methylheptane. What I know about it is that its vapor pressure when it's pure is 233.95 torr. I know its molar mass, because they were nice enough to give it to me, is 114.23 grams per mole. Then they talked about 3-ethyl pentane. And they told me it has also a vapor pressure, which means it must be volatile. Again, if it were not volatile, they would not have given you a vapor pressure. That's really the distinguishing characteristic. So for every substance that is volatile, you're going to have another term, mole fraction times its vapor pressure. So what we know about the mixture is that we have 78.0 grams of this and 15 grams of that. So since I have two volatile fractions, I'm going to need to figure out how many moles and how many moles total. And my total vapor pressure is going to be based on moles of, I'm going to call this one A, call this one B. Moles of A times his pure vapor pressure plus mole fraction of B times his pure vapor pressure. If I had another component in there that was volatile, then I'd have another term. It's just that I only have two substances here. Are you with me so far? All we've done is figure out how many moles of each thing. Now I'm going to substitute in. The mole fraction for substance A should be 0.6828 divided by my total 0.8325. Which means that my mole fraction for B is 1 minus the mole fraction of A, because again, they all have to add up to 1. So you could set up the other one also if you wanted to, but you can save yourself some time. Okay. So 8202 is my mole fraction times my vapor pressure, which was 233.95 for substance A. Sorry. Mole fraction times my vapor pressure. The second one, my mole fraction was 0.1798. And his pure vapor pressure was what? And so there's our total vapor pressure. Now, since everything was given to us in torr, then our total vapor pressure is also in torr. So most of this chapter is very plug and chug. It's just a matter of understanding which form to use and which units are appropriate for it. That's where we're going to quit here, and I'll meet you in lab at about 11.